Okay, so yeah, we've already seen what an equivalence relation is. It's a type of binary relation which satisfies three properties, namely transitive property, the symmetric property, and the reflexive property, right? And from the equivalence relations, you can have equivalence classes, and from those equivalence classes can like partition your set into union of disjoint subsets, right? So that's pretty much all, because we've already seen uh, mostly what an equivalence relation does to a set, right? Um, okay. Yeah, so we've also known what the representative element is. It's an element of a particular equivalence class which represents the equivalence class and the equivalence relation of the class, right? So we'll start from the equivalence relation defined by a map section, right? So if you have a map between sets, and you can have an equivalence relation from this map, which gives you equivalence relation on its domain, right? So here the domain is S. So what this equivalence relation does is defined by identifying A with B such that the image of A is equal to the image of B, right? Yeah. Then we also define the inverse image. We know that that's also called the pre-image. The pre-image is an element of the domain which gets mapped to the codomain, right? So the inverse image of an element in the codomain, such as T, would be the subset of S containing all the elements which are mapped to this lowercase t, right? And how you denote this is in this manner. So the pre-image of T is all the elements in S such that f of S is T. And yeah, unless you have f as a bijective map, this pre-image will not be a map, right? So this is where you have to distinguish things. This can be almost equivalent to writing the inverse of a map, right? So the f inverse of the map f, but that's not always true, right? So normally what you always have is the pre-image is a set, the inverse image is a set, but unless the function that you're taking the pre-image of is bijective, you're not going to get a map, all right? And these are also called the fibers. This is definition that we use quite regularly in differential geometry and algebraic topology. The fibers are the inverse images of a map. Okay, so yeah, let's go through this example, and then we have some proposition on this. So if G is a finite group, we can define f from G to the natural numbers. What it does is takes f of a, so it takes f of a as the order of the element A in the group. So right, so if you have an element A in the group, f of a represents the order of that element. The fibers of this map are the sets of elements with the same order, right? So yeah, naturally, if you take the fiber of let's say 3, you're going to get all the elements of G that have the order 3, right? Okay, so let's now think of, like, right, we saw that if you have a map, you can have an equivalence relation from this map. But if the map is a group homomorphism, right, so if this is a group homomorphism going from one group to another, the equivalence relation on G would be denoted by congruence rather than this similarity, this tilde sign, right? So this is referred to as congruence. So A is congruent to B if phi of A is equal to phi of B, right? So if the images are equal, then your groups are congruent, right? Yeah, and we've seen this in the section on kernels, that the elements A and B of G are congruent. That is, their images are the same if and only if B is in the coset AK of the kernel K, right? Yeah, that was one of the propositions that we proved. Okay, so now we have this proposition which says that let K be the kernel of a homomorphism phi, then the fiber of phi that contains an element A of G is this coset AK, right, of the kernel. These cosets partition the group G and they correspond to the elements of the image of phi, right? So what this is saying is that you can have these cosets, and these cosets are going to partition your group G with respect to the image of the elements, right? So you have the group G, you have the group G prime, and the image of the whole group G is in G prime. So this is the image of phi, right? And your AK is the coset. So all the elements of AK get mapped to phi of A, and all the elements of the kernel of the map get mapped to the identity, right? So what it does, it creates, when you take the inverse image, the pre-image of these, you're going to get these disjoint sets, and they're going to be cosets, but they will partition the group actually, right? So yeah, this is in the case of a group homomorphism, right? So we're going to see something more about cosets and a bunch of propositions relating to cosets, right? Okay, so yeah, we've already seen this before. If H is a subgroup of a group and you take an element A from G, then the subset AH is the left coset, and it contains all the products AH such that H is an H. So the small h are the elements of the capital H, and these set of products form the left coset, right? Okay, so the cosets of H and G are equivalence classes for the congruence relation. Yep. So A is congruent to B if B can be represented as AH for some element H in the subgroup H, right? So you have to prove that this congruence indeed is an equivalence relation. We just claimed here that it is actually an equivalence relation, but we have not proved it. And the proving is pretty much straightforward. We just have to prove that it's transitive, which it is, and symmetry. You can see that B equals to AH, so you can use the inverses of H to show that the symmetry holds. Then reflexivity holds because the H is a subgroup and it has an identity. So yeah. Okay, so we have a corollary, right? So the left cosets of a subgroup H of a group G partition the group, right? So if you have the left cosets of a subgroup, they're going to partition your group in a precise way. Okay, so yeah, Hearn just posted some link to this blog, I guess, relating to the cosets of the kernel. Hearn, can you say something about it? I'll check it out.
I just found this, this series of blog posts very helpful. If you really understand like what this quotient group mean, like from the first two blog posts, I think in the series, the theorem of the cosets of the kernel are isomorphic to the image of the homomorphism. It's almost just trivial, and it also uses commutative diagrams. Because it wasn't trivial to me the first time I read it, to me it's like a big improvement, right? So it really helped me a lot.
Okay. Yeah, it does look pretty cool. Okay, so this is in the chalkboard. Anyone else who's interested, you can check it out. Okay, let's get back to business. So we're going to prove this, that the left cosets of subgroup partition the group, but it's not really anything to prove because the left cosets are essentially congruence relations, and congruence relations are equivalence relations, and we know that equivalence relations form partitions. So that's pretty much it. Okay. By the way, hello Matt. Okay, so now we're going to see a few other things. So yeah, so if you have the symmetric group S3 and you have an element Y that generates a cyclic subgroup, right? So the subgroup is H. It's a cyclic subgroup of Y, and its order is 2. So here you get 3 left cosets of H in G. So these are the left cosets. So it's H equals to 1 and Y. So that will be YH, right? This will be XH. So where you'll have X and XY as elements. And that is equal to XYH, right? And you'll have X square H containing X square and X square Y, and that will be also equal to X square YH. So this is, if you remember what we saw in S3, it was having the elements of these kinds, and they partition the symmetric group into these disjoint subsets. Yeah. So yeah, if you just like try to remind yourself that H is indeed a subgroup, so these two conditions are going to be equivalent in the sense that if you have some B, then it should be equal to AH for some H in the subgroup H. Then B is an element of the left coset of AH, and the left cosets AH and BH are equal. Alright, so these three are equivalent from what we've just proved, right? Because you have the congruence relation between each other. Okay. So yeah, so the number of left cosets the subgroup has would be called the index of the subgroup in that group. So the index is denoted by this notation. So the index of the subgroup, sorry, the index of the subgroup, the cyclic subgroup Y of S3 is 3, right? but when the group is infinite, the index may be infinite too. That makes sense. Okay, so we'll quickly go through these lemmas and their corollaries, and we'll see the Lagrange theorem about subgroup of a finite group and its order, and yeah. So the lemma 2.8.7 says that all left cosets AH of a subgroup have the same order, right? So all the left cosets of a particular subgroup are going to be the same order, and that there's nothing really to prove, because what you do is you multiply A with the subgroup H, right? And you define a map which takes you from H to the left coset, right? So what it does, it takes an element from the subgroup and it gives you AH. And this map is bijective. That's easy to see. And it's also because the inverse exists, right? So inverse exists because you have the inverse of every element A as A inverse in the group G, right? So because the group is well defined, so you have the inverse, and you have the bijective map in the other direction. So yeah. Okay, so the cosets have the same order and they partition the group, right? So that's what we saw. And from here we can get the counting formula. So what the counting formula is that the order of G is equal to the order of H times the number of cosets, and that makes sense, right? If you have the order of one subgroup, you can just calculate the number of cosets. If you have the order of one coset and you can know the number of cosets in the subgroup, you can find the order of G. Right? Okay, so that was the counting formula. It's just counting the order of G by counting the number of cosets. Okay, so the Lagrange theorem, let's see. So the Lagrange theorem says that you have a subgroup of a finite group, then the order of H divides the order of G, right? So, and the corollary, which is pretty much straightforward from there, is that the order of an element of a finite group divides the order of the group, right? Okay, so the proof is again straightforward because we've already seen this previously in a proposition. So the order of an element A of a group G is equal to the order of the cyclic subgroup, right, generated by A, and the cyclic subgroup generated by A is the order of that is something that's divisible by the order of the group, right? So yeah, that works out. And you also have another corollary which says that if you have a group G and its order is prime, so you have a prime order, then you take an element of G other than the identity, then G becomes the cyclic group generated by A, right? So if your group has an order of P, the cyclic group generated by A is isomorphic to the original group, right? Okay, so the proof goes something like this, which is also pretty straightforward. The order of an element, which is again distinct and like non-trivial, it's not the identity, is greater than 1, right? And it divides the order of G, which we've seen previously, because from this corollary, it divides the order of G, which is the prime integer P, right? Because it's a prime, it either has to be 1 or it has to be the integer P, right? But we already decided that it's non-trivial, so it can be 1, so it has to be p, so the order of A is equal to p, and this is also the order of the cyclic subgroup, right, generated by A. So since D also has the order of P, so the group itself has to be equal to the cyclic subgroup, right? Yeah, and what this lets you have is that the groups of prime order are of like one class, right? So they form one isomorphism class, and the class is the class of cyclic subgroups of order P, right? Cyclic groups of order P, yeah. Okay, that makes sense. So then you have the counting formula. When you apply that to a homomorphism, yeah, which we've seen before, that the left cosets of the kernel are the non-empty fibers of the map phi, right? So they are the preimages, and they are in bijective correspondence with the elements of the image, right? So what this gives you is that with the counting formula, the order of G, sorry, what was that? The index of a kernel, right? So the index of the kernel of phi under G is equal to the image of phi, right? And that makes sense because your fibers, the preimages, are in bijective correspondence, so you have the one-to-one correspondence to the image. So its index is going to be equal to the image of the homomorphism. Okay, so now you have a pretty straightforward corollary from there. You have a homomorphism between finite groups, then the order of the group is equal to the kernel of phi times the image of phi, right? And the kernel of phi divides the order of G, and the image of phi divides both the order of G and G prime. So here the kernel of phi is actually the order of the kernel of phi and the order of the image of phi, right? And it all makes sense from the Lagrange Theorem. Right? Okay, so yeah, they give an example of the Sine homomorphism, which I've seen before. So the Sine homomorphism attributes plus or minus 1 to a specific permutation of n elements, right? The Sine homomorphism is surjective, right? So its image has order 2, right? So its image has just 2 elements. Its kernel, as we've seen before, the kernel of the Sine homomorphism is the alternating group, right? And its order is half n factorial. Yeah, there is half the elements of Sn, right? And but it's the order of, yeah, I'm messing it up, but the order of An is equal to half the order of Sn, right? But the next sentence is that the half of the elements of Sn are even permutations and half are odd permutations. So that's why the even permutations, you can like assign either way. The even permutations can be given the sign +1, or the odd permutations can be given the sign -1. Okay, so this proposition gives you the multiplicative property of the index. Then we'll see right cosets and a few of their propositions. So what you do is you have this chain of subgroups starting from G, then having the subgroup H of it, then a subgroup K of H, right? Then the index of K is equal to the index of H times the index of K in H, right? So you start from the index of h in G, then the index of k in H. Makes pretty sense. But let's see the proof. The proof is straightforward, but you have to use the equivalence relations on the cosets, right? Okay. So yeah, so let's say that the index of H under G is M, and the index of K under H is N. Right? So you have M cosets of H in G, right? So you choose representative elements for each coset. So these cosets can be represented in this manner. You have G1H, G2H, G3H until GMH. So you have M cosets like that. And what you do is when you take the union of these cosets, you're going to get a partition of G, as we've seen before. You take the union of the cosets, because the cosets are like disjoint sets in the group, right? And when you take their union, they're going to give you a partition. Okay, so what you do something similar for k in H. So your k in H is going to give you a partition such that subgroup H can be written as H1k union till HNK. Right? So you have the union of these disjoint subsets, cosets. Right? Okay, since multiplication by GI is an invertible operation, yeah. So what you can do is you can like multiply this equation that we just had for the subgroup H, and then you multiply it throughout it with GI. So GIH is going to give you GIH1k and until GIHNK. So this is going to be a partition of the coset GIH, right? And what you can do is if you put these partitions together, wait a second. Okay, yeah. Okay. Yeah, so yeah, someone just called me, so I had to mute. Yeah. This is analogous to how the dimension of a vector space is the dimension of the null space plus the dimension of the image. Yeah, indeed. By the way, is my voice cracking or is it fine? Okay, cool. So yeah, so this was the multiplicative property of the index. Okay, so now we get to write cosets, and then we'll see a few propositions from there. But yeah, I think like this is pretty much straightforward from the definition of the cosets. Nothing much in there. But yeah, we'll go through that. Modular arithmetic is just 1.5 page. That's nothing much. And then in the next lecture we'll see the correspondence theorem, product groups and quotient groups, so that will be more interesting. But yeah, okay, so the right cosets, we saw that the left cosets are when you multiply things on the left side, the right cosets will be exactly that, except multiplication on the right side. There is some static. Oh, not sure if there's something from here.
I can hear you without static.
Okay. Okay, that's nice. Okay, so these are the right cosets. Then you have the equivalence relation, the congruence, as we had for the left cosets, except in the right direction. So A is congruent to B if B can be represented as H, A. So you have the multiplication on the right side. Right. Okay, so the right cosets also partition the group, just like left cosets did, but they are not really exactly the same. So, for instance, as we saw before, if you take the cyclic subgroup Y of S3, the right cosets of the subgroup will be 1Y. Yeah, so that would be HY, right? So the right coset with respect to Y. Then HX, which will contain X and X square Y. So that will be equal to HX square Y. And this will be HX square. So this is, you can see this is different from what we saw as the partition in left cosets, right? So yeah, but yeah, if your subgroup is normal, right? So if your subgroup, if you remember the normal subgroups, if your subgroup is normal, then you're going to have the right cosets and the left cosets as exactly the same. So there, the concept of coset becomes general. Okay. So yeah, we have this proposition where these claims are equivalent, and let's see. So H is a normal subgroup, right? So if H is a normal subgroup for all the elements in H, and all G in G, the conjugates of H with G are also in the subgroup, right? So that's the definition of a normal subgroup. And then for all the G in the group, the conjugate of the group subgroup is equal to the group itself. Okay, so that also makes sense. And for all the elements in the group, the left coset is equal to the right coset. That's just what we said earlier. And every left coset of H in G is a right coset. Well, that's the same. So yeah, let's see. So when you're taking the conjugate of a group, you're actually taking the conjugate of all the elements of the subgroup, right? H. So yeah, they just prove it here. H is normal, so if one holds, the first proposition holds, then it implies that the conjugates are in the subgroup H for all G in the group, right? So what you can do is you can substitute this this left side G with G inverse, right? And this one with G, and what you see is that this also is a subgroup of H, and this is pretty straightforward to see because you're taking the conjugate of H in just the opposite manner, but it's the exactly same thing, right? So G inverse is equal to H. So the conjugates in either direction are a subset of H. So the conjugate itself has to be the set, right? So G inverse is H. This by G and on the right side by G inverse to conclude that H is also a subset of this conjugate. Yeah, right, okay. I messed it up, but yeah, so you just show that they are subsets of each other and thus the sets are equal. Okay. So what this shows is this shows proposition 2. So 1 implies 2. 2 does imply 1. Yeah. So from here, if you multiply G on either sides, we're going to get that. So G and G inverse are going to get cancelled. We're going to get GH is equal to HG. So if you multiply G on the right side, that is right. So you're going to get that the left coset is equal to the right coset. Right. And then in this manner, the third proposition is proved. And proving that 3 implies 4 is trivial, right? So you have to show that 4 does imply 3. So every left coset of H in G is a right coset, right? Okay, so okay, so yeah, we know that the left coset and the right coset always have one element in common, right? So what the element is common is that the thing that you're multiplying, G. Because G, when you multiply the identity on either side, it still stays G. So it's in either of these cosets. So so if the left coset GH is equal to any right coset, it must be the coset must be HG. So right. So 4 says that every left coset of H and G is a right coset. So if the left coset like if you can like have any equality between the left coset and any other right coset, that right coset has to be HG itself. Right? So in this manner, every left coset of H is actually a right coset. Okay, so this is like these propositions are pretty much trivial. You just like have to go through the details and prove them. So the next proposition says that if H is a subgroup of a group G, and you have an element from the group, the conjugate of the subgroup is also a subgroup. Right? Okay. And the second one is if a group G has just one subgroup of order R, then that subgroup has to be normal. The first one is trivial because we know about automorphisms. So alright, so the conjugation is an automorphism, and GHG inverse is the image of H under this automorphism, so it has to be a subgroup. And for B, if it has just one subgroup, you'll see that all the conjugates are going to be like in that subgroup, all the conjugates for all the G's in the group G, right? So that subgroup has to be
can I ask a question?
Sure.
Why is conjugation by G an automorphism of G? I missed that part.
It is an automorphism because when you take I think we should go back to the definition of conjugation because I think they are defined, but the automorphism is again an homomorphism of a set onto itself. So you're taking these elements of G and then you're like wait, do you accept that the conjugation is a homomorphism?
Yeah, that's pretty much.
Yeah, but as you're taking elements of G onto itself again, so no, it's an automorphism.
I was under the impression that we were taking automorphism to mean bijective endomorphism. So bijective homomorphism into itself.
Not
Does that make
really.
sense?
The automorphisms here we're dealing with are just because if you're taking bijective, then it's an isomorphism, but
I think in a Luffy, the notation was endomorphism means a function or a transformation from a set to itself,
yeah.
and automorphism means if it's bijective.
Okay, so then I probably have messed up the definitions. Let me see what Artin does.
Yeah, so automorphism is bijective endomorphism.
Yeah, yeah, exactly. In these, it's the bijective.
But I don't think Artin does the same. Maybe he does it. Automorphism is an endomorphism.
Yeah. So yeah, in page 52.
Okay.
Yeah. So the isomorphisms of the group to itself are the automorphisms indeed. Yeah.
Oh, okay.
Yeah. So you're asking like, why is this an isomorphism?
Yeah.
Let's see.
Yeah. The argument he gives is that it has an inverse function conjugation by the inverse of G.
Yeah, because if you replace
that
G with
makes
G
sense,
inverse, then you can get the inverse map. Yeah.
Okay. Yeah. Thanks.
Okay, so that was about cosets, left and right, and yeah, that was it. Now we are on to the section of modular arithmetic. I guess you guys have seen some of this earlier. Okay, so we're going to define what the congruence in here means. So yeah, you take two integers a and b, and they are said to be congruent to modulo n if n divides the difference of the two integers. So if n divides b minus a, or if you can write b as a plus nk. So a plus some multiple of n, alright? And this is the very first thing that you learn in number theory, right? So how the notation is like this: a congruence b mod n, and you have to check if b minus a is divisible by n. And this is actually an equivalence relation. That's easy to see because you have reflexivity, you do have transitivity. The other thing you'll have a hard time proving, but yeah, it's an equivalence relation. So then again, you have the equivalence classes called the congruence classes, and it's denoted by here at least by bar notation. So a bar denotes all the elements, all the sets of integers that are congruent to a mod n. And these elements are written like this: a minus n, a plus n, a plus 2n, because of this form. Right? So all the b's are of this form. Okay. So if a and b are integers, the equation a bar equals to b bar means that, so if your congruence classes are equal, then it means that a is congruent to b mod n, right? So yeah. So you have this class 0 bar, which is just the set of integers which are multiples of n. So you have 0, n, 2n, minus n, minus 2n, and yeah, all the elements kn such that k is an integer, so the multiples of n. And so this is a subgroup of the additive group, right? And from this you can have the other congruence classes would be the cosets of the subgroup, right? So yeah, the thing that you have to remember that Zn is not really a right coset. It is a subgroup of Z plus, right? It's not a right coset. It's just that you're multiplying the n on the right side for each integer k. So let's see, the notation for a coset of a subgroup H. Now it goes to AH, but using the additive notation for the law of composition is A plus H, right? Instead of like AH, that was when we had multiplicative notation, but as we're dealing with the additive group of integers, so you have A plus H, so but the definition stays the same, right? Okay, so the congruence classes are going to be these sets where the coset is the set of elements A plus Kn, would be again integers of this format. Okay. But yeah, so if you have a modulo n, then you're going to have n congruence classes for this, and the index for this Zn, that is the congruence class 0 bar of the subgroup Zn, is going to be n, and that's straightforward to see. Okay. So yeah, here they show how you can actually add these congruences. So you have two congruence classes, A bar and B bar, by the integers A and B. Then you have the sum of these congruence classes would be the congruence class of A plus B, and their product of these congruence classes would be the congruence class of AB, right? So yeah, so what it says is that A bar plus B bar gives you A plus B bar, and A bar times B bar gives you AB bar, right? And the justification is that so the like equivalence classes, you have different representatives for the class, right? So if they're in the same class, then they can be identified with the equivalence relation, right? So any integer a prime which is congruent to a mod n represents the same class as a does, right? So if you have two elements that are congruent, then they represent the same class. So if a prime is congruent to a and b prime is congruent to b, then a prime plus b prime is going to be congruent to a plus b, right? So, and you prove that in this following lemma. Okay, so yeah, we do this with contradiction. Contradiction, right? Not really. So you assume that a prime is congruent to a and b prime is congruent to b, such that a prime can be written as some a plus rn. And this is because a prime is congruent to a mod n, so a prime can be written as the a plus some multiple of n. And you can do the same for b prime, right? So what you do is you add these things, add these two things, that is a plus b prime. It's going to give you a plus b plus r plus s times n. And what this shows is that you can have the congruence between a prime plus b prime with a plus b, right? And you do the same for the product. So yeah. Okay, so now further we can check that the commutativity, distributivity, and associativity, everything holds for these congruence classes, right? So these are the laws. A bar times b bar plus c bar can be, we can exchange the, you can put the bars at different levels. So you can take the congruence class of this whole b plus c and then multiply with a bar, or you can just take the congruence class of this whole product. So yeah. Okay. Yeah. So this was pretty much it. A bit of using what we have known about congruence and integers. There's nothing else much in it because I think like they do include some number theoretic concepts later, but yeah, here that was it pretty much. I'm not sure, but I've been someone who has done some elementary number theory, like analytic number theory, not algebraic. But I'm interested in algebraic number theory, so maybe after this, or maybe we can replace the what was that, representation theory of the last week of this course with something of number theory. Not sure. The Euler format theorem. Are you talking about that? Right. Yeah, that was okay. So I knew that was the Euler's in a Torsion function. Yeah. Okay, so okay, so if representation theory is interesting, then that's nice. I mean, we don't do much of it. I think we just spend like 2 weeks on it, but at least it's better than nothing. Yeah, okay. We can take number theory as a separate thing. Yeah, I was talking to JP just before you guys joined that after algebra, because we've got already a lot of commutative algebra through this course, we are pretty much fine to do number theory and algebraic geometry on their own. Yeah, the Euler's Torsion function is very interesting. It is something that you get from the Fermat's little theorem, and it was pretty nice to like prove a few things about it when I was doing elementary number theory. But yeah, like if you think about it, like the amount of things that Euler has done in his life is incredible. Not sure how a human can do such amount of things. Okay, so that was on modular arithmetic. We do have time, So, do you guys think we can go through a bit of a Luffy right now? Or if you guys want to leave early, you can do that. But I think we can go through a Luffy in our extra time. That will be nice to keep up with the categorical understanding. Okay. A Luffy. Yeah. Okay, so that was R10. Thursday we're going to see these 3 sections on products, quotients, and stuff like that. But yeah, tomorrow we have the P set. Okay, so let me open, what was that? A Luffy. What was this book that I was going through? By the way, so there was this other book. I don't think I posted this, or maybe I did. I got to know about this book from one of the members here, who is doing his PhD in, not PDE, something else. Yeah, I don't even remember. That was something very abstract. But his professor has written this book, and it's good because of the way it handles things. It doesn't cover a lot of things. Let me find it. Good Lord. This was it? No. Let me remember the author. So the thing is, if you know the other book from topology, so from topology we had this nice book called, what was that? Topology through inquiry. So the good thing about this book is that it is made for teaching yourself things, right? So this book like makes you think, like think about the theorems and the like reasoning behind them. It doesn't provide a lot of proofs, but it gives a lot of examples and pointers about intuition, about the concept. And the same thing was something with algebra, and I'm trying to find what was that. Let me find. Okay, this one. Yeah. Yeah, so this was the inquiry-based approach for abstract algebra. They don't cover a lot. They just cover like rings, some polynomial rings, and groups. Like they don't start with groups. They start with rings and then they get to groups, which is not the usual way you see the treatment. But the good thing about this, as I was saying, is that they give like a very nice way to read and like teach yourself things. So yeah, you might be interested. I might have posted
There's also a number theory version, I think.
For this?
Number theory through inquiry, yeah.
Ah, okay. Yeah. Okay, so let's get to a Luffy. We'll see if we can do some sections from there. So last time we did, what was that? Right, we were doing the products in the category of groups. And the last thing we did was the universal property of the groups, the direct sum on abelian groups. Right. Okay, so now it has a few exercises. I don't think I've done any of them, but it looks worthy to try at least 2 or 3 of these. Okay, so now we're going to see the group homomorphisms with respect to the category, and we'll see like how that happens. And this proposition is something that we've seen in algebra already, right? Okay. I'm trying to see if there's something like different in the way they treat this with respect to arts, because we're not going to repeat the same thing, right? Okay, let's see. Yeah, so the group homomorphisms are morphisms in the category of group between two objects, right? The objects are groups. Okay, so the purely categorical way to think about this is that since the group has zero objects, right? Remember, zero objects. There are unique morphisms from this G to this like zero object, and from the zero object to H, right? In the category group. So if you take the composition, is going to be a unique distinguished element in the Hom set between these two Hom set of the morphisms between these two objects, right? And this is the trivial morphism. Okay, so this is an example of group homomorphism. Okay, so yeah, they also give an example of the group action. Yeah, we haven't seen group action yet. We're not going to see it until 3 weeks from now, when we go to advanced group theory. We're going to see group actions from Rotman. But yeah, so they say this as, in general, an action of a group G on an object A of a category is a homomorphism which goes from the group to the set of automorphisms on an object A. That is, a group G quote-unquote acts on an object if the elements of the group G determine isomorphisms of that object to itself. So this is a more general version of compositions, right? So you have like what you would say, a way of like taking elements from G, and for each element you determine isomorphisms which like go from that object to itself, right? Okay. Let's see. So if the category is a set, this means that the elements of G determine specific permutations of the set A, right? Okay. So yeah, let's try to understand this. You have the group G. You have the set of automorphisms of an object A of some another category C, right? So if the category is that of sets, then what this does is this gives you the specific permutations of the elements of the set A. Okay. For example, the symmetries of an equilateral triangle, that is elements of D6. D6, you remember? They determine the permutations of the vertices of that triangle. That's the permutation of the number of times you can replace the vertices. That is with the S3, of course. And they do that while respecting the composition. So what this gives you is that a homomorphism from D6 to S3. So D6 is the of course the dihedral group, and what it gives you is the group of what is that? The group of like an hexagon, or yeah. So you can, I think, I'm not sure, like Artin doesn't talk about this, but as I've said before, Gaussian gives you these kind of geometric interpretations. The dihedral group should be there. Right, so this is our tetrahedron, and you try to put permutations here and try to rotate this. Yeah. Okay. Yeah, so anyways, so D6 represents the dihedral group of the hexagon. And with this you can have a quote-unquote action on the vertices of on the set of vertices of the equilateral triangle.
I've jumped over to Wikipedia. They're saying that the notation isn't uniform. In geometry, D6 would be symmetries of a hexagon. In abstract algebra, of a triangle. So the subscript is actually twice the number of vertices. I think that here
I think Alufi mentions this, that his notation is not completely, I mean, he's choosing to represent this, but not all authors do that. When I was taught this in university, they used the other notation. So this would be D3.
D3 in the geometric sense.
Yeah, so symmetries of a triangle is D3, but in here is D6, right?
Okay. Where does Alufi say this? I think I missed it.
Let me see if I can find the page.
Okay.
It's page 52.
Okay.
And you have to look at the footnote 11.
Page 52, let me see. Page 52 would be okay, dihedral groups. Okay, yeah, makes sense. So let's see, what else do we have?
See that what they're referring to here is that the order of the dihedral group is 6.
Yeah.
So if you look at the number of elements, it's 6. It's not the number of vertices, but the number of elements in the symmetry group.
That's the difference between the algebraic and the geometric notation. Right.
Right.
Yeah. So the D6, that will be D6 in the geometric convention is the interesting. It's the symmetric group of the snowflake, right? So yeah, makes sense. It will be an hexagon. So yeah. Okay, so we have some few other examples of homomorphisms. The exponential function is a homomorphism, taking you from the group of R with the addition to the group of positive reals with multiplication, right? Ordinary multiplication. So e to the power a plus b will give you e to the a times e to the b, right? But if you take this to be a bit more abstract, you have the exponential map at the level of groups, generalized groups. So right, so G is any group on this exponential map. What it does is it takes an element, so it takes an integer a from Z, and it gives you G to the power a. So it gives you an exponent a. It gives you an exponent for the given integer, right? And this is an exponential map, and it's a homomorphism, right, from Z to G. And this element G, which you're taking the exponent of, right, generates the whole group G if and only if this homomorphism is subjective, right? And yeah, so if they're subjective, every like the whole group is going to contain just the exponents of G. Okay, so one of the examples of this they say as the quotient function. So the quotient function pi n takes you from Z to Z mod nz. So that will be taking an integer a and mapping it to a times the identity under n. So this represents the identity in nz, right? The multiples of n. And so that what that gives you is an element a, right? So this is an equivalence class in nz. Right? So what you're trying to do is this quotient function takes you from an integer and it gives you this x power of this these multiples. Interesting. Okay. So if m divides n, so so here they're talking about like how if you have some m and then the n multiple, so m is like in the equivalence class of these multiples of n, and if that generates this whole set, then that means the GCD of those m and n is 1. Okay, so if m divides n, then you can like have this pi nm. So pi nm goes from z mod nz to z mod mz, right? So from the multiples of n to the multiples of n, right? And you have this diagram. So this looks a lot like projection, but it isn't. So you have pi m from z to z mod mz, pi n to z mod nz, and you have pi nm going from these two, going from here to here. And if this diagram commutes, then pi nm of something from here, so that will be like this, will give you exactly an element here, right? And it's an exercise to prove that this actually is a well-defined function. Okay. Let's see. Okay. So if we have two m's, m1 and m2, that are both divisors of n, so they both divide n. So then what you have two homomorphisms, pi n m1 and pi n m2, going from nz, multiples of nz, to the multiples of m1 and m2z, right? And hence to their direct product, of course. Direct product in the categorical sense, I believe. So for instance, since 6 is equal to 2 times 3, there is a homomorphism which takes from multiples of 6 to multiples of 2, product multiples of 3, right? So yeah, so explicitly what it does is it you have these 6 elements in here, 6z. So you have 0, 1, 2, 3, 4, 5, 6, and then they get mapped onto ordered pairs of multiples of 2 and multiples of 3. So 0 in the equivalence class of multiples of 2, again in multiples of 3, so 0, 0, 1, 1, 0, 2, then 1, 0, 0, 1, and 1, 2. So that's how you do it. Okay. I'm kind of not entirely clear about this, but it does make sense. And this is a bijection, and they're going to prove it right now, but what this means is that it's an isomorphism, right? So you can write each of these multiples sets, so like the mod of some multiple, you can write them as in terms of these direct products. So that's something nice. Yeah. Okay. So they're asking, is there a non-trivial group homomorphism from C4 to C7? Yeah, so I think they said it's somewhere in chapter 1, when we were doing sets and categories, that the number of set functions you're going to have from Cn to Cn is m to the power n. So here it's going to be 7 to the power 4. That will be 2401 set functions, but we have to, because it's a homomorphism, we have to make sure the law of composition, the operation is satisfied and preserved. Think about it. You have to find out on what conditions you can or cannot have this homomorphism.
You know that the image is going to be a subgroup of C7.
Yeah.
Since C7 has prime order, the only subgroups are the two trivial ones, either the whole thing or just the identity.
Yeah.
The image of C4 has got to be one of those two things.
Okay.
And the image of C4 cannot be the whole C7, right?
Yeah. That's
C7 is bigger.
Okay. Nice. Okay, so homomorphism and order. This is something we've already seen in Arten, so I don't really want to repeat this. Let's see if we have anything else. A group G is cyclic if it is isomorphic to Z or to Cn. Okay. Homomorphism of abelian groups. We didn't see anything on abelian groups, so let's see. We have the category of abelian groups, right? And that's somewhat better in the sense it's more special than the category of groups. So let's see. The set of homomorphisms from G to H for any two groups GH is a pointed set. They saw they were saying this before, how it's a pointed set containing the morphisms from the objects G and H. But in terms of abelian groups, the Hom set is itself not only a group, it's an abelian group containing morphisms from G to H. You see, that's kind of interesting, isn't it? So the operation that you have on the Hom set of abelian groups is inherited from the operation in H. Okay, so let's see how that works. So you have two group homomorphisms going from G to H. Then you add these two homomorphisms in this manner. What you do is you take phi plus psi acting on an element of a group that is equal to phi of A plus psi of A. So this again is well defined as a homomorphism, as a group homomorphism, right? Yeah, because you can have this phi plus psi acting on any element A plus B in Okay, acting on an element a plus b, then you have phi of a plus b plus psi of f plus b, and yeah, we can know that because phi and psi are homomorphisms, so you can write them in this manner. But but this can also be written as phi of a plus psi of a. Let's see, phi of a plus psi of a. If H is a commutative group, that is an abelian group, then yeah, it doesn't matter like how you apply the operation like on which sides of it, right? So if you open these parentheses, that will be phi of a plus phi of b plus psi of a plus psi of b. You can like drag this here, and you'll have phi of a plus psi of a, and then put the parentheses, because you know, whether you're taking the plus here with the psi or you're taking it here doesn't matter because of the commutativity, and because it's a like group operation, it's already associated. So using the commutativity, you get here, and from here you can you have phi of a plus psi of a plus phi of b plus psi of b, and this is equal to phi plus psi of a plus phi plus psi acting on b, right? So you have this, and this makes it a group homomorphism. Which one? Phi plus psi. So that itself is the map, and it's a group homomorphism. So what this means is that this group homomorphism is actually is actually an operation that would be on the Hom set. Alright. So this Hom set contains all these abelian groups, and using this plus symbol where you like add two homomorphisms and you get a group homomorphism from there. From here you can say that this thing actually works as a group, right? So let's see. The associativity holds, of course. The trivial homomorphism would be the identity. The trivial homomorphism, yep, just like you can have in case of phi and psi. The inverse, that is the inverse of like elements of a group, right? So the inverse of this group homomorphism is defined by this manner, right? So it gives you this, and when you like compose it, apply the operation, you're going to get the identity, right? So here it's not the inverse as in the bijective map, right? So your phi is the group element, and you're taking the group inverse. Yeah, so what they're saying is that if you're like even if like G is not commutative, if you just have commutativity from H, this Hom set like in the category of groups is a group, right? But if H is commutative, then like you can also have this in the category of sets, right? So H to the power A will give you the Hom set of all the morphisms from A to H in the category of sets, right? But yeah, so this is kind of like, it is straightforward, but not sure if we're going to use this a lot. But yeah, so that was group homomorphism in the category of group and in the category of abelian groups. Okay, so we still have a few minutes, luckily, so we can do something with free groups, and free groups are interesting. So yeah, we can talk a bit about that. Okay, so yeah, we've seen free groups before. Not only free groups, we've seen free products, right? When we were talking about direct sum in the category of abelian groups, right? So the intuition or the motivation here is that you have a set A, whose elements have no special group theory property, in the sense that it's just a set, and if you construct a group from this set, it contains A in the most efficient ways. So in the sense that it contains, it arranges the elements of A in the most efficient way, right? Okay. So let's so for if it's a trivial group, if it's just an out set, then you'll have the trivial group, no wonder. But if you have, let's say, a singleton, this single element in the set A, then right. So f of A, that's like from the singleton, you're not going to get the trivial group, because the trivial group must contain just the identity, right? And yeah, then like if you have the identity in the set A, like that would already mean that you have some kind of group theoretic structure to it, which we said we don't really have that on A. So what you do to have a group is that you construct an infinite cyclic group from this element A, right? And these elements are formal powers, A to the n. So you take powers of integers n, right? And it looks something like this. We've already seen this, the cyclic subgroup, right? But here, before we saw that as like you take an element of a group and then you form a cyclic subgroup out of it. But here we're just taking an element and then we're creating a cyclic group which contains these powers of these element A, right? So so these powers are distinct, and you can like this multiplication, like which creates these powers, it has to be done in such a manner that the exponential map must be an isomorphism, right? So the exponential map will always take from the integers and will give you the power to that integer, right? Okay. Right, so this was what I was saying in the sense of free groups before, like you just like blindly take elements and then you combine them. So what this means is that you have the powers are distinct, but there is nothing special about like taking each element. So it doesn't matter which element you're taking, the fact that like you have this cyclic group, which is just the group of powers, it doesn't have to satisfy any specific condition, right? Other than the fact that like when you take the 0 power, you're going to get the identity that has to be there, because otherwise you're not going to have an identity. You need an identity for a group. So yeah. So the goal is, what we've done is, you take a singleton, and from there you have the free group of A to be the infinite cyclic group from the singleton, right? So what you can do is you can have like sets containing more than singletons, right? So sets containing different elements, and there you're going to see how we can arrange the products in this quote-unquote free manner, right? Okay, so they give you this task that to formalize the heuristic motivation given above and construct a group f of A for every set A, right? Right, so yeah, so they're trying to make you think about the generalized notion. So for example, instead of having one element, if you have two elements A and B, then what will f of A look like, right? Like, what will the cyclic group look like? The cyclic group containing two elements. Well, you can see this pretty easily. You'll have, first of all, for the identity, you'll have A0, B0, that will give you the identity E. Then you'll have A0, B1, you'll have A1, B0, and in this manner you're going to like create the powers of different elements. Right? And this gets more and more kind of complicated as you have more elements in the set A, right? Because you'll have different permutations. Okay.
So it's like all possible combinations of
Yeah,
A and B.
Exactly.
In essence.
All
Okay.
possible combinations and all possible combinations of their powers, right?
Mm-hmm.
It's interesting because you do this a lot in algebraic topology, at least in the very early part. You need to do free groups of loops and stuff like that. The idea is you can like arrange these maps in any manner you want, and you're going to get something interesting from there. So free groups are very interesting. So they have this universal property about free groups. Let's see what we can see here. Yeah, we still have 15 minutes. You can see. Let's see. Okay, yeah. The generalized idea can be taken by this universal property. So if you have the set A, this group f of A will have to contain A, right? So A is a subgroup, is a subset of f of A. So it's going to, not even a subset, it's like all the elements of A have to be in f of A, right? So what you can do is you can have a category. So you have this curly f, and on top of that you have A, and these objects are going to be pairs JG. So J is going to be an element, J is going to be a morphism from this, not really a morphism, it's going to be just a function, set function from A to G. So, let me see. J takes you from A to G. A has the elements Okay, so it assigns you elements in G from elements in A. Okay, then what you do is you do this for different groups, right? So J goes from A to G1, then J1 goes from A to G1, J2 goes from A to G2. So you have these pairs, J1 with G1 and J2 with G2, right? So now these are going to be your objects in the curly FA, right? And as usual, you're going to have commutative diagrams for these. So you have G1 to G2, so that will be a group homomorphism for this to commute. So phi is a group homomorphism, and you have J2 and J1 going from A as these functions, right? And yeah, so this helps us think about morphisms and like groups in general as like objects of a category. Okay. So the free group f of A on A will be an initial object in this category, right? So so what this lets us have is that if this is an initial object, you can take the mapping from A to f of A, and you'll see this in the most efficient way, which means that like you can see this what was that? I'm forgetting this. Most efficient in the sense that any other way you map A to this group can be reconstructed from this map, right? So okay, so in the language of universal properties, how they state this is that f of A is a free group on the set A if there is a set function going from A to f of A such that for all groups G and set functions f from A to G, there exists a unique group homomorphism from f of A to G. See, this is where you have the abstraction of category theory, right? Let's try to understand this. Maybe this is the last thing we'll see, but yeah. So what you have first of all the set A. Then f of A is going to be the free group if you have the function j which goes from A to f of A. So it must include A, right? So it must contain A in the free group. And on top of that, for all the groups G and for all the functions you can take from A to these groups G, there exists a unique group homomorphism from f of A to G such that this whole thing diagram commutes, right? This is the universal property in the sense that this works for every set A, any group G, and it is the key property that will let you have a free group, right? Okay, so yeah, and this makes sense. So if your phi is an isomorphism, then you're going to have the same group, but so it is defined up to isomorphism. But does f of a exist? Does it exist? Well, we've already said a lot about f of a before it existed, but we have to show that there indeed exists this kind of unique homomorphism. Let's see. So if your A is like a singleton, just as we saw before, then your f of A will be just the set of integers, right? Will be isomorphic to the integers, because you're just going to have the powers of A and the powers of A in the free group will just form the integers. So now, yeah, that's now what you do is you have the first step is find this J, which takes you from A to Z. So it takes the element A to the identity in Z. Okay. I
think here he's thinking about 1 as a generator for Z.
Yeah, A to the 1 it means, right? Because the
so it's not the identity on the set, right?
Is the 1 in Z. I mean, it's the identity in anyway, but yeah, it's still one number integer. Okay, so now you have some group G, then you have a function from A to G, which takes an element which just gives you the elements small g, which are the images of the singleton, right? F of A is equal to G. Now if your singleton is in G, right? So if A is in G, then there is a unique homomorphism which takes you from the integers to the G. Because A is in G, so you can have a unique homomorphism, because phi of 1 is always going to give you phi of 1 will give you phi of J of A, and J of A J of A gives you the identity. Okay, that was that. So phi of 1 is equal to phi of J of A, because J of A is the identity, 1, and that is equal to F of A. So because that's how we defined phi circ G, isn't it? Yep, because this is F, so phi circ G. So first J and then phi will give you F of A, right? And that is equal to G. So you can do this for 1. So phi of 1 gives you G to the power 1. So phi of 2 will give you G to the 2. Phi of n will give you G to the n, because phi is the unique homomorphism. And phi, as you've seen before, is the exponential map, except is a lot more general. So these infinite cyclic groups do satisfy the universal property for free groups over singleton. So what we did is just prove that this cyclic group that we earlier defined is indeed a free group for the singleton with respect to the universal property that we that we saw. So that was all about the categorical way of doing some group theory. We're not going to see much, maybe, yeah, we can try and devote the free time we have onto these things, because, you know, in any way it's better. Okay, so yeah, that was it. Thanks everyone. It was around like 2 hours. Yeah, thanks for sticking around. We have the PSAT discussion tomorrow at 3 p.m. UTC, and we'll discuss the PSAT, which is interesting this time. So yeah, see ya tomorrow. Thanks for joining.